Welcome to the video on intermolecular forces, the last video for 2012. Yay! Okay, this is the culmination of everything we've been doing this unit so far. We talked about how to draw molecules, and then we talked about whether the molecules have whatever kind of shape they are, if they're linear or bent or whatever. And then we talked about whether the bonds in the molecule are polar, and then we talked about whether the molecule is polar or not polar, and all that is to get to this. What is holding molecules together? When you have a substance, let's say you have, some water. Well, that's not just one molecule of water, it's the whole bajillion molecules of water. And those molecules of water have to hold together. If they don't hold together, it wouldn't be liquid water. They would be all over the place. It would be gas. So in order to hold together, there has to be some kind of force between the molecules. So if this is a molecule, and this is a molecule, there's got to be something holding those two molecules together. If there isn't, like I said, it's a gas. So we're going to talk about what kinds of things hold molecules together. They're called intermolecular forces. That makes sense. Inter means between molecules. So between molecules, the forces between molecules. And they're abbreviated IMF. So I'm going to write that out more frequently. All right. IMF is based on attractions. Attractions between positives and negatives. We've done a lot with positives and negatives, with partial positives and negatives, and all that kind of stuff. There are two things that tell you how strong the attraction is. One, the strength of the positive or negative. What does that mean? Well, are we talking about a full positive versus a partial positive? So is it ionic or is it polar? How strong is this positive charge? Obviously, the stronger the positive charge, the stronger the attraction. Then also the duration of the charges, which ties back into the strength. If you have something like this, that means that cation is positive 100% of the time. If you have something like this, then that means it's sharing the electrons, and when the electron's far away from it, it is positive, but it's something less than 100, but greater. So the delta positive is less than 100, but greater than 50. So if it's 50-50 sharing, then it's not getting a delta negative or delta positive at all. But if it's somewhere between 50 and 100, then it's getting a delta that's partially positive. So how long does the electron spend with the atom versus spend with the other atom? And as I said, the IMF tells you whether you are going to be a solid, a liquid, or a gas. The stronger the forces between the molecules, the more tightly they hold together, the more likely you are to be a solid. And that's why when you have something that is a solid, you can't get through it. Those molecules are holding together so tightly that nothing can pass through them. If you have a very weak set of intermolecular forces, we're talking about a gas. And you can pass through gases very easily. You do that all the time in the air. Air is a gas. It's very weakly held together. And liquids are somewhere in between. It's easier to penetrate through a liquid, like I could stick my finger through a glass of water, but it's not as easy as a gas. It takes more energy to do that. And we're going to talk about that in another unit later. Now, there are four types of intermolecular forces, going from the strongest to the weakest. Ionic bonds are the very strongest, then hydrogen bonds, then dipole attraction, then dispersion forces. Now, these last two are called van der Waals forces. Guess which guy discovered them? All right, so it's a Dutch guy, Dr. van der Waals, and he discovered dipole attraction and dispersion forces, and the name after him. On the quest homework, dispersion forces are sometimes called instantaneous dipoles. Instantaneous dipole. So just be aware of that. This term and this term mean the same thing. Okay, notice nowhere on this list are covalent bonds. You're like, well, we've been talking about covalent bonds all unit. Why aren't they on this list? That's because these are the list of the bonds between molecules, intermolecular. Covalents are the ones inside the molecule, intramolecular. So covalent bonds are very, very strong, even stronger than ionic bonds. But because they're not between the molecules, we're not going to be talking about them right now. All right, so let's talk about each one of these in turn. First, ionic bonds. Ionic bonds exist in ionic compounds. Ionic compounds are made of metals and nonmetals. For example, sodium chloride. The metal gives its electron away to the nonmetal, and therefore the metal becomes positive, the nonmetal becomes negative. This is a full positive, and a full negative is 100% of the time, so it's very strong. That's why these are the strongest, because they have the highest charge. Second, hydrogen bonds. Hydrogen bonds are very specialized intermolecular forces, and they only occur when you have hydrogen, and the hydrogen has to be bonded to a certain element. You have to have a hydrogen bonded to a nitrogen, a hydrogen bonded to an oxygen, or a hydrogen bonded to a chlorine. Those are the only times that you have hydrogen bonds. Just because there's a hydrogen there does not mean it's going to be a hydrogen bond. For example, water has hydrogen bonds because it's oxygen bonded to hydrogen. Here's the deal. Hydrogen is a very small element, the smallest we have. It is only one proton and one electron, and that's it. When hydrogen's electron is at a different atom, hydrogen's just a proton. Well, a proton, that's positive, that's fully positive. So when hydrogens are getting a delta negative, or I'm sorry, a delta positive, that delta positive is closer to the 100 end of the scale than it is to the 50 end of the scale. And so this is one of the strongest partial charges that exist. Hydrogen has a 2.1 electronegativity, oxygen is 3.5, so obviously oxygen will be pulling the electron away, and the electron will spend more time with the oxygen than it does with the hydrogen, and when it does that, hydrogen is a partial positive charge, but when I say partial, I mean almost 100%, and so therefore it is very strong. But it only happens when hydrogen is bonded to an extremely electronegative element, nitrogen, oxygen, or chlorine. And so this is what holds water molecules together. So what you get is, this. Okay, so you have this water molecule that has a delta negative on the oxygen and delta positives on the hydrogens. And then, of course, water is not just one water molecule, it's a ton of water molecules. So let's have another water molecule over here. And we'll have another one over here. And so on and so forth. We just got a bunch of water molecules. Well, this hydrogen is also slightly positive, and so it'll be attracted to the negative, slightly negative oxygen of a different water molecule. And this hydrogen will be attracted to it, and this hydrogen will be attracted to that oxygen, and so on and so forth. So all the hydrogens are going to be attracted to all oxygens of different molecules. And we represent intermolecular forces with these dashed lines. This right here is a covalent bond. It gets a solid line. This is a hydrogen bond, abbreviated H bond. It gets a dotted line. It is not nearly as strong as a covalent bond, but it is pretty strong, strong enough to hold the water together. Third one, dipole attractions. Dipole attractions happen when you have a molecule that's a dipole, that has, but not dealing with the hydrogen bonds. So let's say we have this molecule here, carbon monoxide. We did this one in class, and we determined that carbon monoxide is a polar molecule. It's got a partially positive charge, or a negative charge. It will not be quite this positive. It is more positive than this positive. So it's not quite as powerful as a hydrogen bond, which is why it's further on down our list of strength on the intermolecular force. But it is permanent. So we will have another carbon monoxide molecule here, and maybe another carbon monoxide molecule over here. And, you know, carbon monoxide molecules can be all over the place. Well, the delta negative oxygen on one carbon monoxide molecule will be attracted to the delta positive carbon on the other molecule, and so on and so forth. And so all of these molecules will be held together that way. Lastly, and most weakly, we have dispersion forces. Dispersion forces exist in non-polar molecules. Something like our lovely fluorine that we did in class. Okay, so here's the deal. These two electrons are being shared equally. However, at some random moment, these electrons might happen to both be on one fluorine instead of the other fluorine. So when that happens, as these electrons are moving around, they're moving here, they're moving here, they're moving here. At the moment that they're over here, that makes this fluorine slightly positive. Slightly negative when the electrons are there. That makes this fluorine slightly positive. Now, those electrons are going to continue to move, and when they do, those go away. So these charges do not last. They appear in one instant and they're gone the next instant, which is why they're also called instantaneous dipoles. So this thing becomes a dipole molecule, but only for a fraction of a second. And then the electrons move on, and that's gone. But in that fraction of a second, if you have one fluorine molecule that's got the negative and the positive, and you have another fluorine molecule that just so happens to have a negative and a positive, then in that fraction of a second, the negative end of this fluorine molecule will be attracted to the negative end of that fluorine molecule. But like I said, the electron's going to move on from there, and as soon as it does, the charges go away, and this attraction breaks. So these molecules do not hold together very well. They hold together a little bit for fractions and fractions of a second, but they do not hold together for very long. And so this is a very weak intermolecular force, and these things typically be gases. Typically. Now, so let's just go back. This is going to happen. Let me get another color. Blue. Ionic bonds happen when you have metals and nonmetals, meaning you have ionic bonds, ionic compounds. Hydrogen bonds happen when you have hydrogen bonded to nitrogen, oxygen, or fluorine. Dipole attractions happen when you have dipole molecules, which is why we spent last class figuring out whether the molecule is going to be a dipole or not. And instantaneous dipoles, or dispersion forces, happen on non-polar molecules. So in order to figure out what type of intermolecular force is holding each one of these kinds of substances together, you need to be able to draw it, you need to be able to figure out the polarity of the bond, and then you need to figure out the polarity of the molecule. If you wind up with a nonpolar molecule, it's going to be held together by dispersion forces. If you wind up with a dipole that doesn't have hydrogen bonded to oxygen, nitrogen, or fluorine, then you're going to have dipole attractions. If you draw your molecule and you see that it has hydrogen bonded to a nitrogen, oxygen, or fluorine, then it's going to be held together by hydrogen bonds. And if you calculate your electronegativities and you get a difference that's 2.1 or greater, it's going to be an ionic bond, and therefore it'll be held together like that. So these are the intermolecular forces available to various kinds of elements. Thank you.